Hope everybody's doing well today. Good afternoon. My name is Matt Halley. I'm a member of the engineering and marketing team here at Buckley Associates. Before I start the webinar, I just want to make sure I say a few words. First of all, thank you all for participating today. Take some time of your day and spend some time to learn with us today. It means a lot to us here at Buckley to that you're here, because we're really putting some effort into making sure these webinars are informative and of good value to you. Really ever since March, we've been making an effort to provide these webinars for you guys. Usually we spend some time, the engineering and marketing team spends some time going into your offices to provide these webinars. As of late, we've been doing it virtually. You can find all of our past webinars on our YouTube channel since March. So if you guys find this useful, maybe you want to check out some of our old webinars as well. But today we're going to be talking about design strategies and product solutions and high bay applications. So if you guys have any questions, feel free to send them into the chat. Looks like yeah. And anyways, so send them into the chat. We'll field them there. And yeah, so also we'll be muting everybody. Sometimes there's some feedback. So Sherry, I don't know if you can hear me, but if you can help me with that, that'd be great. So, so let's get started here. So my name is Matt Halley. I'm your host today, and here I am. So just a little bit about me. I'm from Akron, Ohio. You know, same as LeBron James and Steph Curry. A lot of talent coming out of Akron, Ohio. So I got my Bachelor's of Science in Mechanical Engineering from University of Akron. I spent some time in design internships, and then with another rep firm out in Akron, in that area. I formerly was a Greenheck and Price rep out there, and then I moved to Boston in 2018. So I've been working with MEP firm accounts inside and outside of Boston ever since then. So I'm actually one of 10 Buckley points of contact for you to reach out to for any HVAC design. I think I still hear some feedback. If everybody could please mute themselves, that'd be great. So, all right, but not me, please. Okay. So anyways, let's get started here. So today we'll be talking about high bay applications, like I mentioned. So first off, we're going to define what those are. We're going to talk about the methods of HVAC design in those spaces, and that will typically refer to mixed systems, destratification, and radiant heat in those systems, and then finally displacement ventilation. So first off, what is an high bay application? So Aire Standard 113 does a great job of helping us out with air diffusion in a space with the ADPI, Air Diffusion Performance Index. That's a great point system measurement for air distribution into space, and it works really well for 9 or 10 foot spaces with the ceiling. However, that means it does not work for high bay applications. So we really need to take what we know about design in those spaces and apply those to a high bay ceiling. So at Buckley, we really believe any space above a 12-foot ceiling is considered high bay. So that could really mean anything from atriums, auditoriums, gymnasiums, airport terminals, libraries, really anything with a high bay system, with a high ceiling, could be considered a high bay system. So this is, just about as high as it gets. This is actually the Detroit Red Wings facility out in Michigan. This is a duct sock system, which we'll talk about here in a little bit. You can see the duct socks here coming off. I think you guys can see my pointer here. So this is the duct sock system coming off this metal duct, which comes from the equipment. It helps disperse that air into the whole system. There would eventually be another one down below, but this is the type of system we'll be talking about. We can also look at, say, this swimming pool. You can see this big ass fan here that helps with destratification. However, there is ventilation elsewhere in this space, and that is another great example of a mixed system. Another good example of a mixed system is an airport terminal. High bay ceilings. Airports are usually pretty large. These are some examples of some Punkah louvers over here. We'll be talking about what those are and how to design around Punkah louvers. And then finally, here's an example of an industrial space. Warehouses, can't forget warehouses and other industrial spaces. Those are also typically high bay spaces. and this is a displacement system, which we'll be talking about near the end. You can see these displacement diffusers supplying air to the floor. So before we get into any of that, let's talk about what the methods of design. So in any design method, it plays a large role in energy efficiency, which, you know, right off the bat, that's your operating costs. And then obviously any awards you can get with those and incentives you can get those with those from the government. So that's all great. You can save all the money in the world, except if your occupants aren't comfortable, then you really didn't succeed. So you want to make sure you have good occupant comfort and indoor air quality as well. So all of these things need to be considered really from the start. So once you have your structure, some of these methods of design we'll be talking about are then limited. So this is why you need to talk to people like us at Buckley to help you figure out what that system will be and how to design around it. So any of these methods of design really are split into two different types. So you got mixed air systems or displacement systems. Within mixed air systems, it can be either fully mixed, that's the most common, and within that, you can actually use destratification, which assists a fully mixed system. And then finally, you could actually have a partially mixed system, and that's usually from an underfloor air distribution, which is what UFAD means right there. And as a displacement system, you're actually purposefully creating a stratified space. That could be from underfloor systems, overhead systems, or even sidewall diffusers. So in any space, though, you really have 5 performance mandates. Those are temperature, air movement, humidity, quality, and sound. So those are all governed by different ASHRAE standards. ASHRAE 55 for thermal environment conditions, ASHRAE 62.1 for ventilation, and those are all governed by the energy standard, which is ASHRAE 90.1. So in any space, before we talk about how to condition the space, it's really important to understand what you're actually conditioning. Any space has an occupied zone. This is where people will be standing or sitting, and that's 6 feet from the floor, 3.3 feet from any exterior wall. It's not shown here in the picture, and then 1 foot from any interior wall. So that's really important because when you're talking about a high bay system, this is actually a very small fraction of what a high bay system is. So the question then becomes, how efficiently can we actually condition this zone specifically? And then more importantly, what is the zone air distribution effectiveness? That's that's the long version of ventilation effectiveness. So that's just a measure of how effectively that zone air distribution uses the supply air to maintain acceptable air quality in the occupied zone. And that's actually just defined by ASHRAE 62.1. So all that to say, it's really just a ratio of your total space outdoor airflow divided by your occupied zone outdoor airflow. So when we look at this table, also in ASHRAE 62.1, you'll see that the top 3, these are all mixed systems. Actually, the top 4, sorry, maybe top 5. So really, anytime you're supplying cool air in a mixed system, you're going to get a ventilation effectiveness of 1.0. And that's just saying that air, the amount of air you're providing to the space as a whole is an equal airflow as what you're trying to provide to that occupied zone. So it's interesting, once you start supplying warm air, if that warm air is actually above 15 degrees differential of the space temperature, you're actually getting a ventilation effectiveness of 0.8, which means you're actually supplying more air than the occupied zone requires. So your effectiveness in that space is actually a lot less than it could be. Now, if you're looking at a displacement system down here, see this 1.2, that 1.2 is actually the minimum ventilation effectiveness. So this is considered, so in other words, you're actually only conditioning that occupied space, that occupied zone. So you're supplying less air than that total space is than is needed for that entire space. So let's look again at mixed systems. So before we get into high bay mixed systems, let's first understand exactly what we'll consider, at least for the sake of this presentation, what a low bay system is. So I mentioned earlier that ADPI does a great job of helping us understand what a low bay system, how to define or design around a low bay system. But basically the goal of a low bay system, or really any mixed system, is that you're trying to mix that airspace as much as possible. But you got to consider that in that occupied zone, you don't want to exceed 70 feet per minute. In fact, you're supposed to target 50 feet per minute max in that occupied zone of your airflow velocity. So, and you also want to keep that draft temperature between -3 degrees to positive 2 degrees of the set point. So really, the goal here, at least in this example, these diffusers are throwing this air along the ceiling and then the wall to then mix into that comfort zone. So they're higher velocities up here, which actually helps with which actually creates a Coanda effect. So that air is going to hug the ceiling and then the wall because there's a low differential pressure against that ceiling and wall. You're actually using the Bernoulli principle, kind of like an airplane, where that air will actually hug against that ceiling and then the wall. It'll throw itself down along the floor and then mix into that space at an ideal low velocity around 50 feet per minute. Okay, and you also the goal really is to mix this air into this comfort zone as well as possible. So ADPI, we could get into that, but we're not going to, because that's not what we're talking about. It could work for a 9-foot or 10-foot ceiling, but it will not help for high bay, partially because there's not going to be any ceilings once you get to a high bay. So just to be clear, so we understand, once you the idea here is, okay, take a look at these two pictures down below. The red represents heat, the blue represents cold, and in this space you have a thermostat on each wall, on the wall of each space, right? It's in the same spot, and that thermostat is actually right in that mixed zone right there, in the stratified zone right in the middle. So it actually doesn't know that it's a stratified space. So this diffuser is not performing effectively enough to mix this system. So you end up with a very stratified space, and eventually it could result in a waste of energy, thermal discomfort, and indoor air quality, because you're not actually bringing that heat down, or you're not mixing that space well in general. So this is bad in a small system, but it's pretty easily fixed. But in a high bay system, you could end up with quite a bit of stratification, and you don't want that. So let's keep going. Oops. So mixed air systems in a high bay application. Let's apply that theory and bring it into a high bay application. You're no longer using your diffuser that is going to hug the ceiling, because there might not even be a single thing near the diffuser that you could hug. And not only that, but you would need a lot longer throw for it actually to reach the floor like it did in the low bay system. So this is why we need to look at jet theory. So it's kind of shown down here in these two pictures, but basically your diffuser now is acting as a jet. There's a lot of different types of diffusers that can act as a jet. You know, typically you see something which is called a Punkah louver. And if anybody that doesn't know what a Punkah louver is, it's actually the same diffuser you see above you when you sit in an airplane. If you reach up to adjust that, that's actually a Punkah louver. We could also talk about air nozzles, drum louvers. A drum louver might not look like a jet, but it actually acts as a jet when it's in the space. So it'll basically be throwing that air out with a long throw. It could also be called projection. It'll have some drop, and it'll have some vertical spread and a large angle of discharge. So, and also as that jet stream is going, it'll actually induce air as it moves. So it can actually induce really a minimum of 4-to-1 air volume. So it'll actually grab that room air and mix it as it drops into the space. A really good way to think about what that jet stream is doing is to think of a gardening hose. So when you're watering your plants, it's kind of like, think of that as, let's think of an airport terminal. Let's say this is on the wall of an airport terminal. That supply air is coming out at a constant volume. It's slowing down, but as it's slowing down, it's actually inducing air, and then it's dropping into that terminal zone. And then in this case, that terminal zone is this plant right here. That stream is spread out, and it's dropping at a interesting rate, so that once you're into this zone 4, the terminal zone, you're dropping down into about 50 feet per minute in that occupied zone. So let's look at an example. By the way, this concept applies similarly to horizontal and vertical patterns. So if you switch from a horizontal pattern, as shown here, into a vertical pattern, you're actually just adding that drop to the throw. So let's look at a vertical application then. So projection or throw, as we defined it previously, is a measurement of distance where, if you see, look at this example here, you have a 10, an 18, and a 26. So that is actually at 10 feet, it's going to be 400 feet per minute. At 18 feet, it's going to be 200 feet per minute. And then at 26 feet, it'll actually be 100 feet per minute. So that's the velocity at which, so that's the distance at which it will be a certain velocity. So in this case, with these high bay jets, you're actually dealing with 400 feet per minute, 200 feet per minute, and 100 feet per minute. Note though, with typical smaller applications, let's call them low bay again, you're actually usually dealing with 100 feet per minute, 150 feet per minute, 100 feet per minute, and 50 feet per minute. But with these jet nozzles or other high bay systems, you're typically dealing with higher speeds. So that's why it ends with 100 feet per minute. So also note that when you're actually combining these columns of air, you end up with more mass. So these four would have a combined mass in the middle, and because it's combined and has larger mass, it can actually go further. So, and obviously though, that considered, it would actually have a smaller angle of discharge as well. So in an application where, so let's say you have a 60-foot ceiling, this one on the right would actually be a great selection to use, considering it has a 51-foot throw at 100 feet per minute, 100 feet per minute. So just, let's say 3 feet above that occupied zone, you're at about 100 feet per minute, and it will slow down considerably, as you can see right here in this transit terminal zone, because considering this is speed right here, it'll drop in speed right as it hits that occupied zone. So this would actually be a great application or a great selection for a let's say a 60-foot ceiling. So any questions so far? Nothing. All right. So, and just so we're clear, I mean, the idea here is that you're really just treating that occupied zone the same as you would in a small system. It's just now you're trying to reach that at with a longer throw. It's really what it comes down to. So we can do this with like I mentioned, we can do this with all sorts of diffusers. We have Buckley represents quite a few diffusers that we could do this with. From the previous example, this is an Aire nozzle. There's a number of different Aire methods we could use as well. Oops. Jet nozzles. This is actually called a Punkah louver as well. We can offer this as well, or drum louvers. So this is just an idea of what we're working with here. So if we're not going to do, so let's get away from talking about diffusers. This is actually an interesting turnkey solution to a high bay mixed system, where this actually is the diffuser. So if you look at this example below, you have in a typical application, you would have your metal duct, your diffusers, your connecting ducts, your flex duct, your dampers. All of those could actually be replaced with this duct socks right here. So duct socks actually acts as a diffuser. It's a really labor-saving installation. You don't have that weight. You don't have all that material hanging from the ceiling. And actually, duct socks has a dedicated design team to providing a perfect air distribution in the space. So just reach out to us, and we can actually tell you exactly what you would need in that space. So here's an example of a shop drawing that a contractor would receive after the job is won by duct socks. The duct socks design team will actually provide you exactly what orientations you need. So in this case, the size 13 vent at 5 o'clock and 7 o'clock will provide this airflow at of a velocity of 150 feet per minute. Sorry, actually 50 feet per minute, 100 feet per minute, and 150 feet per minute per this right here. So this is just an idea of what we can provide with duct socks. It's a really great solution for high bay applications, like I showed you in that Detroit Red Wings arena. So another example of a cool arena application. This is a TCU Coliseum renovation. So and this is actually a good example because this shows what the previous high bay design looked like. They had metal duct with these duct grills throwing air into the space, right? So It would condition the space. It would mix the space relatively well. But notice how it's actually throwing above the occupants. It's throwing into the middle. So they do end up getting, mixed air, but it's not as efficient as the design that Ductwork came up with, which they actually ended up putting this 60-inch diameter ring in the middle, where it would actually throw at the occupants as well as into the middle. So it provided a really well mixed system. It turned out great. As you can see, this ring right here has these linear vent orientations right here, where actually it's throwing at the occupants as well as into the space to mix that system. Here's another great example where this is actually another combined application. So over here in the wall, we have a linear vents that are, something like a Price linear bar diffuser that is actually just throwing air up the wall. But say in cooling, you're actually throwing this air out of this duct socks at the pool area instead. So you could actually have both. It works really well for any type of high bay application where you have a mixed system. So speaking of throwing against the wall, another great duct system that we have available is Blue Duct. This is a direct bury underfloor or underground duct that is actually made of high density polyethylene. It's very resistant to mold and mildew as it's air and water tight, and it's R10 equivalent per the NSF P374 air duct thermal efficiency standard. So really what you're doing here is you're providing yourself a duct system in the structure so that you can actually keep that duct system away from the ceiling, and it's a really good way to just provide your supply air to where you need it. So in this case, just like the application before, you're throwing that air up that wall. So this is for a gymnasium area. You can do it. We actually use this a lot in displacement as well, which we'll get into. But this is also, really anytime again, this is something that you would want to talk to us about from the start, because obviously that would be really tough to put in afterwards. So let's talk about destratification. Rolling with the same idea of, this can be used in any high bay mixed system. In fact, this can even be used in some smaller height ceilings as well. But destratification can come in really two forms. You have high volume, low speed fans, which are HVLS fans. We can also do it with jet fans, which we'll talk about in a second. But either is great for both heating and cooling, because you're sending that heat that gets trapped up above to the floor in the cold months, and you're actually providing an evaporative cooling in the hot months. So evaporative cooling is basically just elevated air speeds. So the idea of evaporative cooling actually came from milk farms or dairy farms out in Kentucky a while, back in, I think, the 80s, where they realized that their cows would actually provide more milk if they were more comfortable. So they put these big fans in the dairy farms, and actually that elevated airspeed helped cool down the cows, and they were able to produce more milk. How they figured that out, I don't know, but it's working for us well, because it actually reduces air conditioning energy, or AC energy consumption, as you provide that elevated airspeed at the ground. So Big Ass Fan says, actually, for every set point you raise your thermostat, you can actually save 3 to 6% energy costs on your equipment. So let's look at that. Let's look at how that actually affects the comfort of the space. So here's an example on the left where you're using AC only, and your set point's 75 degrees, and your airspeed's 20 feet per minute, which, 20 feet per minute is, you wouldn't detect that in any sense at the occupied zone. Now, you would feel, if let's say we move that airspeed up to 110 feet per minute, and we increase that set point up to 80 degrees. So now you just increase that set point 5 degrees. So according to Big Ass Fan's theory of 3 to 6% per set point, you're actually increasing that, you're decreasing your energy load by 15 to 30%, which is a huge savings in the long run. And you're actually still getting the exact same conditions as you would, and it's still satisfying ASHRAE 55 by doing that. So let's look at that on, oh, by the way, here's the cooling effect from elevated airspeed. You can see that it's like a logarithmic function here, but and the inflection point is really around the 300, 400 feet per minute range. So let's actually apply that range to another another scenario. So I don't know if you guys have seen the CBE thermal comfort tool, but this actually shows whether or not your space with the conditions you have is ASHRAE 55 compliant. So in this case, we have an operating temperature of 75 degrees and your airspeed is 20 feet per minute. Let's get crazy and actually let's increase that 10 degrees. So at 85 degrees set point, you're basically not even using your air conditioning equipment, but you do use your HVLS fan or jet fan, and you're actually supplying a 300 feet per minute airspeed at the ground. That is actually still compliant with ASHRAE 55 because it's still in this band of compliancy right here. Pretty interesting, but how does this actually affect heating as well? So in heating, you're actually, like I said it before, you're actually sending that heat to the floor. We call it free heating. So all that heat gets trapped up above, and you're sending that heat down to the floor. And no, you're actually not reverse heating. So that's actually a myth that I grew up thinking as well. My dad always told me to flip the fan when you're in the winter months. But apparently it's actually better to send that heat to the floor instead. You actually use less power consumption on that fan if you were to do it that way. So that said, another thing to think about during heating. So remember when we talked about ventilation effectiveness before, where in heating you're at 0.8. So if you use some method to get that heat into that occupied zone, so like I mentioned, if you get that heat down to 4.5 feet above the floor, you actually get that ventilation effectiveness ratio of 1 instead of 0.8. So in this example, on the left, we have no destratification. We're supplying 250 CFM. 50 of it is being short-circuited, so you need to exhaust 250 CFM. However, the occupied zone only needs 200 CFM. So in this application with the HVLS fan, we're actually mixing that system well. We're sending all the heat down to the space, and that air from the equipment now reduces by 50 CFM because now you're actually using all of the air, and you can actually reduce your equipment load that way. So there's a real example of how to reduce your energy load just by ventilation effectiveness on its own. So if you guys haven't noticed, those were all big ass fan. That was all, the big ass fan material that I was using there. They're the market leader in HVLS fans. That's why we've partnered with big ass fans. They have a wide range of commercial, industrial, and residential models. Really easy and intuitive to control options to integrate into your mix system, and always let us show you the difference as well. The bottom left is an example of the Spec Lab layout tool that we have. That's actually that's a real example of a job I've done previously with an engineer where he actually wanted to see exactly how the space would look in terms of airflow speed in a space. So we were able to provide that with their CFD tool in the Spec Lab layout tool. So if you ever have a layout, please reach out to us and we'll show you exactly how it would look in the space. Here's another example. This is just a quick example of how these can be used. This is a brewery. This is a commercial. I think it's the Essence fan or the ISIS fan. It's sending air to the space. Notice how you also have this ventilation supplier as well. This is obviously a mixed system. You still need ventilation. It's just a matter of mixing that well, so you can actually take some of that load off from that ventilation system. So let's talk about jet fans. So Aire fans, Aire is a company that we've partnered with to provide jet fans. They're actually the ones that really pioneered this technology. They're really good for dead spots for narrow targets. So instead of high volume, low speed, they're actually sending a column of air down where it hits the floor at about 150 feet per minute, and it will actually circulate that air and destratify it that way. So this is really great, like I said, for narrow targets. So anytime you have aisleways, this is a really good application to use. So something like grocery store or a warehouse with racking in it. This is a great, or even another application we've used these in is something like a field house where, a punt return in practice might hit a big ass fan. You don't want that. or say like a gymnasium where they're going to be playing volleyball games. You don't want the volleyball to hit a big ass fan. You can put these up in the rafters instead, and it can still send that destratification. You can still accomplish destratification just without the big ass fan flying around. So also really easy to control. There's some really great EC. There's EC motor options. Also a really good control option, the Smart Triac controller with the AC induction motor instead. There's actually even a mobile app available where you can control up to 100 fans at a time. So let us know if you're interested in that. We can come up with a layout for you. Also, this is interesting. This is something that, so Aire has been doing this way before the pandemic started. I should mention this because it's an option. This phi cell, it's called photohydroionization. It's a type of UV where it actually sterilizes the contaminants on contact as that air is moving through. They've been doing this for like clean rooms and other applications where the occupant really wants to make sure the air is clean. They've been doing that way before the pandemic started. So this is an option from Aire. I don't know if you guys have an application for that, let us know. And also along those lines, Big Ass Fans has been able to provide Haiku, which is their residential fan, but it can be used in commercial applications as well. They have an uplight for it, which typically provides, you know, an architectural uplight, but now they've actually been able to retrofit that and provide it new with a UVC light instead. So that UVC light basically cleans the air as it's going through. So if you have any interest in that, just let us know. And finally, they've been able to also add some bipolar ionization to some of their larger fans and directional fans as well. So something to consider as facilities are starting to open up. It's good. It could be a retrofit application, but also if you guys have clients that are interested in something like this, let us know. So TWA Radiant Panels. Maybe you guys have heard this name before. They're really the leader of radiant panels, and they can actually do radiant heat and cooling in a space. Typically, they're actually a division of Price Industries, by the way. We've been familiar with this company for quite a while. We've been using them as a provider through Price for a long time, but just recently, we've actually become the exclusive representative for TWA. So we use these quite a bit when we actually have decoupled heating and cooling systems. So what that means is basically you're providing the heat completely separately from your cooling system. So especially in like a destratified system, so like what we're just talking about, if you have a space where a lot of your cooling is coming from that evaporative cooling, and say you need a supplementary heat, a great option would be radiating that heat to the floor with a radiant panel. On the other hand, a great transition here is that we actually use these for most of our displacement ventilation products, displacement ventilation systems. And we'll talk about that in a second, but this bottom picture here is actually an example of another displacement ventilation system in a lab room. So this is a displacement ventilation diffuser, and over here we have we have radiant panels throughout. You see these right here, where this is actually radiating that heat to the floor. So what that does is that heat actually hits the floor, and you're not messing with your system in terms of air movement. You're just simply sending that heat to the floor. It heats the floor, and then that heat comes that way. So pretty cool how it works. Decoupling it keeps that ventilation effectiveness higher in the displacement system. So let's talk about them. On the left here, obviously we have our mixed system that we've been talking about, but now we'll be talking about what this is right here. And remember that thermal plume right there, because that's induced air from this diffuser. So displacement ventilation. This is where stratification is actually the goal. There should not be any mixing whatsoever, because once you start mixing that system, you end up with losing your ventilation effectiveness. So what you're doing is you're actually supplying 63 to 68 degree air at this face of the diffuser so that it just falls out along the floor. It pulls along the floor, and it actually finds heat sources where it'll be naturally convected upwards into the stratified zone. So you're actually trying to return air for between 78 to 85 degrees. And you're actually trying to basically keep an 8 to 10 degree differential temperature in that space. So like I said, you're really just trying to create. You're introducing this air at a very low velocity. The neck velocity of this diffuser may be like 700 to 800 feet per minute, but it's going to slow it down with a baffle inside to down to 40 to 50 feet per minute max. It's like I said, it's going to pull along the floor. It's going to find heat sources, move up, and then be exhausted as high as possible. So why do that? The main reason is you really just get better indoor air quality, but we'll talk about it in a second. You get really good ventilation effects as well. So like I said, that conditioned air finds heat sources like this person here. It'll be naturally convected up his body. He'll breathe it in and he'll breathe out air, which is going to be hotter. It's going to naturally just exit that occupied zone with all the germs, viruses, CO2, whatever, all the things you really don't want to be in the system, and then it will be exhausted out. So in a mixed system, however, it would just keep mixing and eventually it'd be exhausted out, but it could stick around in that space for a while. So that's why there's a buzzword about this type of system going around called a one-path system. You have the supply air coming out. It's going to be one path. It's going to meet the occupant. He'll breathe it out, and then it'll be exhausted outside. So it's really ideal, especially for times like these where you don't want your occupant sick. Occupant performance increases drastically, actually. So there's actually parents of kids at a school that are asking their school what type of ventilation system they have, especially recently, for a number of reasons. One, they don't want them to be sick. Sorry. Hey, Charles, I'll get to your question in 1 second. Sorry. One, you don't want them to be sick. And two, you don't want them to be absent. And three, every 400 parts per million increase in CO2 level actually results in a 21% decrease in cognitive test scores. So that's like, in general, your occupants will be higher performing. So it's a lot of benefits to this. Charles, what's your question? So honestly, from what I've heard about reversing the ceiling fan direction, I'd say that if you can, the reason that it's less efficient to do it that way is because you're throwing the air further. So you might not need to throw the air that far to get that heat to the occupied zone. So that's why really there's no reason to go in the reverse direction. You can, especially with the technology we have, not only with VFDs, but EC motors, the modulation of that fan could be turned down enough so that you could reach the floor with that heat, so that you wouldn't need to go reverse at all. I know that most manufacturers still leave that as an option. I think it's partially because people think that that's what they need to do. But according to Big Ass Fans, that's not what you should be doing. You should really be sending the heat to the floor with an HVLS fan in general. I hope that answered your question. Okay, cool. All right, so let's continue on. There's a lot of great benefits to displacement ventilation. Not only, like we were talking about, indoor air quality, but it really deafens the space as well. So it's a lot quieter. And the reason because you don't have really high velocities of air coming out of those diffusers like you would in a mixed system. Not only that, but the static pressure in that system from the balancing damp. Well, there is still a baffle, so there would be static pressure, obviously, but you don't hear it as much as you would like a diffuser with its own static pressure plus the balancing damper behind it. And then also the thermal comfort that comes along with a higher supply air temperature is much better, considering you're not going to be feeling a 55-degree air temperature at any point. Normally that 55-degree air temperature in a mixed system would have mixed a bit anyways, but you're supplying a lot higher temperature, so it wouldn't be uncomfortable and there wouldn't be a draft because it's not going fast at all. So it's a much better thermal comfort as well. So this is really great for high bay applications, partially because, so I was going to also mention, by the way, so this is a concert hall. As you can see here, you have displacement ventilation along the back, but also in front of this stage. I mean, they wouldn't put that there if it was going to be a problem. I mean, this is a concert hall where noise is very sensitive. Not to mention, let's look at the ceiling here. This is a beautiful ceiling, and the architect would be really bummed out if you had to put a spiral duct grill right there. So it's really I mean, this space specifically was so ideal, but let's look at the volume of the space in general. This, I don't know how tall the ceiling is, but if you think about the proportion of where the occupied zone is compared to the space in general, let's remember that ventilation effectiveness ratio there. So the total space, right, divided by the occupied zone in terms of outdoor airflow, um, that's a huge ratio. It's complete. So small spaces, you're getting a minimum ventilation effectiveness of 1.2, but for this large space, it's going to be much greater than 1.2. I wish I knew the actual number here, but I can tell you that they're going to be saving a lot of energy on that space, and that's really where the benefit comes from. So the economizer opportunity too. I mean, it's really, so imagine especially in a season like what we have now, you end up with a lot more opportunity for economizing because your supply air is between 63 to 68 degrees. So supplying that air, you'll have a lot more opportunities to do so throughout the year than you would in a typical system. So it really, between that, the ventilation effectiveness, there's a ton of certifications that you can get from doing a displacement system in general. Now that said, it isn't just something that you can just throw into your space if it wasn't built for it. This is why you need to talk to us on the foreground of this project. So it really must be discussed on the structural level. We have very flexible designs. In fact, 70 to 80% of displacement ventilation projects actually use custom features. And I can say that from my own experience with doing tons of displacement ventilation projects with Buckley since I've moved here 2018. So just in the past couple of years, I already have a net zero school that's going to be built in the next few weeks, actually. And it's looking really cool. It's a net zero school, and it's all based on displacement and those TWA Radiant Panels. So like I said, most of these systems end up becoming custom, but we can provide standard displacement diffusers as well. All types. We have wall mounted, ceiling mounted, heating and cooling models, industrial models. And keep in mind, these are engineered products, right? It's not just it's not just a diffuser dumping air into the space. This air must be precisely controlled. There's baffles behind this that must slow down the air significantly and really provide that air at a calculated rate. So be careful when to my engineers out there, and contractors, be careful when competitors are trying to provide their products, because you need to make sure that is engineered for this space. And that's actually why it's so important to talk to people like us on the beginning of these projects. So let's talk about heating with displacement. To be honest, we always recommend decoupling that heat, okay? And the reason, because look at this up here to the right. So this is an example of an overhead displacement diffuser. So this air is being dumped into the space, and you will have good ventilation effectiveness there because it's going to pool on the ground, and you're going to get that pooling, and it's not going to be mixed into the system. However, in a heating application, now you're throwing that air against the wall, and as it hits the ground, what's the differential there? If it's hot enough, it's just going to raise right back up, as you can see down here. So look at this bottom picture here. So 2 to 10 degree cooling. So let's say you have a negative 2 to 10 degree, negative 2 to negative 10 degree cool air. That's going to pool on the ground, no problem. And then from 0 to 5 degree heating, which isn't really heating that much, you're going to be kind of it's kind of going to be floating around the space. Eventually it'll make its way up. But if you're hot, to the point that it actually will heat the space, it's just going to raise right up. You're not even going to get heat into the space, and that guy right there is not going to feel it. So that's why we recommend decoupling the space. You end up with, we would recommend a radiant heat method like the TWA Radiant Panels we mentioned before. You could do something like a fin tube radiant heater, a fin tube heater, and that's going to use natural convection, but even that will still send air, the hot air, into the high part of the space. There's some other methods we could look at, but this is the gist of it. Just be careful with heating in ventilation, in displacement ventilation, and the ventilation effectiveness that results from it. Hey, Lizel, could you clarify what outlets you're talking about, please? I'll gladly do that. I'm just not sure which one you mean. Maybe, oh, maybe this one. Okay, so yeah, let's show you guys. So this is what I was talking about. In a application like this is actually the diffuser right here, believe it or not. So it doesn't even look like it, right? But this is actually using an architectural perf where so just for reference, anytime you have an architectural perforated, you say you want to have a custom feature, if your architectural perf, okay, thanks. If you use an architectural perf, make sure it's 50% free area or greater, and it will not affect the performance of the displacement diffuser. So this one actually looks a little tighter than that. They might have calculated how it will affect their performance, and we could do that as well, but we would recommend typically having a 50% free area. So that's this one right here. And then this is actually the same example as this picture right here. This is a stage where the displacement diffuser is right in front of it. And then right here, this is actually the diffuser right here. So it's pretty cool. They were able to mask it that well. In fact, I actually have another project going on at Logan Airport where we use totems. So they actually have in this Logan Airport project totems where the architect wanted to put Wi-Fi and some other electronic equipment in the totem. So they actually put that above our displacement diffuser and then wrapped it all in an architectural perforation so that it could be dumping air into the space, but also serve as like a Wi-Fi router. It's pretty cool. Okay, so let's keep going. So like I mentioned, be careful with heating. We'll help you work through exactly how to get that decoupled heating. But like I said, just try to keep it decoupled. That's the main point here. But we can do heating from these, but we'd always recommend not doing it. So displacement's a huge, almost like a passion project for the Jerry Price. In fact, he's actually the president and CEO of Price Industries, and this is a huge push for Price. They're very proud of their portfolio. And the main reason being is one, it's super energy efficient, and two, you're actually creating a really clean working environment for the occupants. And it's just, why not push that as hard as you can? So they're really proud of their portfolio. This is actually right in their home base. They're actually from originally Winnipeg, Manitoba, and this is right downtown in the Manitoba Hydro Place. Pretty cool application here. Another really big high space. Here's the San Francisco International Airport, Terminal 2. Another really good example of a high bay displacement application. And finally, here's another good example. This is a casino. So the rest of this casino is actually underfloor, but anywhere they could, they would do displacement diffusing, displacement ventilation along the walls. So you can have combinations like that, but and along the bar here too. Oops. So finally, I want you guys to know too that we can provide the equipment on these projects as well. It's really important that you get that equipment correct so that you're supplying that 63 to 68 degree air with dehumidification. So in a typical application, we could provide something like a GreenHeck energy recovery DOAS unit. We would do like a RVE, GreenHeck RVE. That's what with energy recovery. We can do without energy recovery, but the whole point of this is to cover energy. So we could provide it like this. This is an example where we could do modulating hot gas reheat to bring that dehumidified air up to your reheat temperature. We can do these up to 18,500 CFM. We have 16:1 direct furnace turn down, and all types of other really great features with this. I don't want to spend too much time on this, but we can provide you a great unit for that. But another thing, so typically what we see on a displacement application is what we call a dual wheel unit, or a unit that's using a desiccant wheel. And this isn't necessarily a dual wheel unit state point diagram, but it does show what a desiccant wheel can do. And actually, Novel Aire is one of our manufacturers that actually provides OEM wheels to big companies like Trane and some other big unit manufacturers, but we actually have them as an exclusive manufacturer for their units, and we can provide these on these types of systems. So, by the way, this is actually another great type of unit to consider for like a chill beam system, another sustainable building product that we can offer. And the idea here, and just to put it very clearly, let's say your start point is A, and you cool that air down to point D with a DX system. Typically, you would just cool it down to say 55 degrees, and you reheat that air with the modulating hot gas reheat or wherever it may be up to your point C. In this case, it shows 75 degrees, but typically it'd be right down here. Same conditions, same idea applies though. So with a novel air unit or a desiccant wheel unit, where you'd also have another enthalpy wheel up on the other side of the unit, this is actually where you would be able to cool it down to point B and then use the desiccant wheel to shortcut all that enthalpy that you would require to cool it down to D. You could drop it all the way back down to C. So that's where the desiccant wheel comes in handy. You actually end up with quite a bit of enthalpy difference there. So that's why we'd use something like a novel air unit for this system. We can provide you that selection as well. So that's it. So thank you everybody for your time. Any questions? Feel free to jump on the mic too and let me know. If not, I appreciate your time. I hope you guys got something out of today. I'm going to be following up with this PowerPoint and some other follow-up information. Feel free to reach out to me if you have any questions about our design, and I could either help you with that if you're my client, or I could put you in contact with somebody who could be your point of contact for Buckley. And yeah, hope you guys all have a great day. Stay tuned for the next one. Hope you guys liked it. Thanks. Bye.